Okay, so as I was saying yesterday, we have this Onsager conjecture that maybe now we should call Onsager's theorem. Okay, so we are looking at solutions of the incompressible Euler equations, which I keep writing in the following way. And I explained yesterday at least some vague motivation why this part is correct. That is, if V is Hölder continuous with alpha above 1 over 3, then the total kinetic energy is a constant in time.
But you may not have uniqueness, right?
But yeah, it's open. It's open, yes. So if you compare to the isometric embedding problem, of course, there it's true that we have a much worse threshold. But above that threshold, this 2 over 3, we actually have the uniqueness, the rigidity, but that's because of Pogorelov, right?
But here, when do we start to know that it's unique?
C1. Well, almost. I mean, Lipschitz is already enough, and actually, if kind of you have something like which fails by a log, then it works. And essentially, it's because when you're comparing two different solutions, there's a Grunwald type argument, and this Grunwald type argument is very brutal, and you're using kind of the modulus of the derivative, essentially, right? So, yeah. And unfortunately, there's no Pogorelov around to use this to prove uniqueness. I mean, you have to say that part, of course. So when we do this rigidity theorem, right? So then at a certain point, we use Pogorelov stuff is big chunk of theory in this book. And
what did Pogorelov say again?
Okay, so Pogorelov has a theorem of the following type. If what he calls the extrinsic curvature, okay? And the extrinsic curvature is pretty much what I described you yesterday. You could think about it as the area distortion of the Gauss map, defined in a very weak way, okay? So essentially, if you have something like a C1, the boundary of a C1 manifold, and this area distortion is positive, Pogorelov tells you actually that that stuff is convex. That's the theorem, right? And so what we are doing in there is when we are C1 2/3 plus epsilon, we are proving that you fall into this Pogorelov assumption, where you can apply Pogorelov's theorem. And Borisov's proof back in the 50s was the same. So he needs 4 papers, but after these 4 papers, then he's in Pogorelov's assumption, and he uses it as a black box. Now it's the same for us. Our proof is a couple of pages, not anymore 4 papers, but then you use Pogorelov, and Pogorelov is a pretty substantial amount of work, right? And that's also why I was saying, in a sense, the fact that this area distortion matches, right? So the theorem we have above 2/3 is that the area distortion of the Gauss map matches the Gauss curvature. And there is a higher dimensional version of this that you can still prove. Only in higher dimension, then you will not be able to use it because you don't have Pogorelov even there. So in a sense, it's really kind of the conservation law which looks like this, more than the rigidity. But who knows? I mean, maybe actually there is uniqueness under that assumption. So that's, I think, absolutely terra incognita. That's really not clear. Okay, so and the other part is actually a correct statement is that there exists V in C0 alpha for every alpha less than 1 over 3, which do not preserve the kinetic energy. Now that's V, not you. Yeah, and really the correct statement is there exists, right? Because actually there are examples where you have this type of regularity and the energy is conserved. So the fact that you're low regular doesn't mean necessarily that the energy has to be dissipated or not conserved. Okay, and what I want to give you today is a feeling for, how you can actually try to approach this theorem and why. So from above, I gave you a vague idea why this 1 over 3 is a good threshold yesterday. So a similarly vague idea, I want to give it to you for why actually this threshold makes sense even from below, okay? So essentially, I will give you a wrong proof in which I'm ignoring tons of technical details and technical problems, and that wouldn't be that bad. But then the proof is really wrong because literally there is some major obstruction to make it work in the way I told you. But this is how we started. And I hope also to convey kind of the idea that the way we're approaching this problem is potentially, might be potentially used in a lot of other situations. Okay, it's a kind of model iteration.
But can I ask one other question? Which
Yeah,
I guess,
yeah.
Does this have something to say about Navier-Stokes in some limit?
I would love that. No.
I mean, even conjecturally?
Maybe, so what I could hope, what seems realistic, so that is something that I actually proposed to one student and postdoc of mine. If you put a viscosity, fractional viscosity, which is not too strong, then maybe you can still do something like that. But of course, you would still produce solutions of, a hypodissipative Navier-Stokes, which are still kind of badly behaved solutions. They wouldn't be classical solutions. So there is one main thing which, in my opinion, we don't understand here, which is telling you that it needs much more understanding if you want to, for instance, hope to show that some of these guys, their limit of vanishing viscosity. I don't know whether they could. I don't even know whether they could. But certainly you have to do something because if it is a limit of reasonable solutions, say Lie solutions, right? So the energy has to go down. And the way we are approaching the problem, we don't see the time arrow. I mean, the way we are actually approaching the problem is only working on Euler. We could reverse the time, and the energy would go up if the energy before was going down. So, and you don't see in our iteration where the time actually comes into play. And I think until we understand that, it's difficult to believe that you can do anything with Navier-Stokes. Okay? And what I was saying is that if the viscosity is sufficiently weak, what I believe is that if the viscosity is sufficiently weak, it will look more similar to Euler from this kind of badly behaved point of view.
Fractional viscosity.
Yes, yes. And it's actually known that if the fractional viscosity is below a certain threshold, for instance, you don't have any Caffarelli-Condivenberg type results, and then it might be rather irregular. Okay. Okay, so what I want to do is I want to set up an iteration mechanism like the one I've set up for kind of differential inclusions and like we have seen for Nash. And this iteration mechanism is going to produce a solution of the Euler equations. And then I want to discuss why actually you might hope that this iteration mechanism is creating a solution which is Hölder continuous with an exponent which is less than 1/3, and also why you might hope with this iteration to get an energy which is non-constant. Okay, so that's what I want to do. Okay, so therefore what I want to do is I want to kind of, first of all, measure in some sense being an approximate solution of the Euler equations. Okay, and for this reason I'm introducing this system of partial differential equations, which in our paper we call Euler-Reynolds systems. And the reason is that it looks very similar to some closure problems in the theory of turbulence, where instead of having 0 over here, you have some kind of stress, which maybe comes from some averaging or some weak convergence of solutions or things like that. So, and now everything is in the smooth category, as in all the iterations that we saw before. So these guys are smooth. And this R circle Q is a 3 × 3 symmetric tensor with trace equal to 0. So that's because of the dot. R circle Q of x and t takes values in the space of symmetric matrices 3 × 3, and then it's trace free. So why it's trace free? Because if I have a part of the trace over here, right, so I can take the trace out, and that will actually give me a gradient, which I can essentially push back into the pressure. So now you might ask, what is the motivation for measuring the distance to be a solution of the Euler equation in this sense? Actually, there is a very natural motivation. I mean, if you think about, again, this relaxation procedure, if I take a sequence of solutions to the Euler equations, and they are converging weakly, right? If they are converging weakly, VQ tensor VQ will not converge to V tensor V in the limit, okay? But there will be a relaxation mechanism. So somehow this R circle Q, you can think about it as the difference between the weak limit of the product and the product of the weak limit, in a sense. Okay? And I'm just taking out the trace because I always know that the trace I can stick it in here. Okay, so and now what I want to ask myself is the following. So I'm imagining I have a very smooth field, VQ, a very smooth PQ, and a very smooth R circle Q. I want to produce a new one, a new tripole, where the size of this gets substantially reduced. Okay? And the idea would then be that I keep iterating this procedure, and along the iteration, the tensor over here is going to 0. And if the tensor over here is going to 0, I will converge to an actual solution. Okay? And then after I have set up this basic iteration mechanism, I want to discuss how regular I can hope to achieve. So how regular is the solution? I mean, what I can hope as a maximal regularity for the limit of this sequence. And then finally, why the energy should be kind of something that I can set up actually freely. Okay? So the first thing I want to understand is, therefore, how to split a tripole which is giving you a much better approximate solution. And as I was emphasizing before, so now actually these guys are fully smooth. They're C infinity. So all computations I'm going to do, they're fully justified. I don't have to care about that. Okay, so now if you remember what we were doing in the first 2 lectures, okay, so it looks very natural to just say, I want to add something which oscillates sufficiently fast, okay? So let me kind of, in a sense, abstract what Nash is doing. I mean, Nash is just using very specific functions. And actually, what happens over here is that I will not be able to use very specific functions like sines and cosines. I really have to solve a PDE, which is complicated. So I just want to kind of abstractly look at Nash as he's adding something which looks like this. So some function, I mean, I will have some kind of master function, big W, which depends on the value of VQ, and then the value of R circle Q over here. And I will call these 2 guys, so these 2 entries for W, the slow variables. And then I have a fast oscillation. And just to remember that we are at the step Q of the iteration, let me put a little q over here. Lambda q x lambda qt. OK, so now this is kind of the ansatz that I want to plug in. And I want to understand how I can choose actually this big W in such a way that I get a new tripole for solving the problem with a much smaller R circle Q. Okay? So PQ will have a similar ansatz. Actually, wait. This I should call lambda q plus 1 because we are the step q plus 1, right? So because I'm producing the next velocity. Yeah. So that's where, for instance, the notes would be useful if I were looking at them, which I'm not. OK, now you could ask, how do I define actually R circle Q plus 1? And now here's the first interesting observation. So if I want to solve this equation, right? I mean, you see that this equation is hugely overdetermined. So what I can do is, if you give me 2 fields, VQ and PQ, I can actually find a field R circle Q by inverting the divergence. OK, so that I can always do. In fact, it's even worse than this. Not only I can do, but I have quite some freedom. So I have to fix a gauge. OK, so one thing which I'm not going to tell you is how I do actually this. But there is some basic elliptic theory so that I could define R circle Q plus 1 as an operator. Let me call it curly R, applied to dt VQ plus 1 plus divergence of VQ plus 1 tensor VQ plus 1 plus gradient of PQ plus 1. And in fact, if you define this operator correctly, it's essentially some Hodge theory. you actually find an operator which is elliptic and which is giving you nice estimates when you make this inverse. So this is a kind of inverse of the divergence. It's like divergence to the -1. Okay, essentially. And now we try to understand whether, I mean, this operator spits me somehow what is the error, so it's a unique way it's determined, and then I will try to understand whether I can make it small. Okay, of course, if I do this, right, I will take care of the first equation. But then you notice that it is the divergence of VQ equal to 0. Okay? In fact, if I make this ansatz, I certainly will not satisfy in general that the divergence is equal to 0. So here I want to put a correction. So let me call this correction WC. Okay, so this correction is added in such a way that I'm divergence free. So this WC is going to be a similar operator which I'm applying to the divergence of this. Okay, so now this actually is important that we discuss how it can be done. So
you haven't defined the big W.
No, and I'm not going to define them.
You know they are?
So yeah. I mean, in the end, somehow I cannot define it to you because it's going to be a huge amount of computations. You have to go into the proof and so on.
How do you
what I want to do is I want to make some computations and I want to determine some conditions for big W and P, so that a certain thing can be done. And that's somehow the value of the method that I'm telling you, because it's not dependent on the Euler equation. So I mean, if you approach a certain problem in PDEs in this way, you can do it, and you will derive other conditions on big W and big P, or similar master functions, depending on the PDE that you are actually dealing with. Okay?
So you haven't told us what the conditions.
I'm not going to tell you. I'm going to derive some conditions.
Okay.
Then we are going to see that if these conditions are satisfied, then you prove the Onsager conjecture. And where actually the problem really is that these conditions can be satisfied. So the method fails because the conditions that we will find are too restrictive of big W and P, and there are no solutions. So then the proof of the conjecture is actually that although I cannot solve those conditions exactly, I can find approximation which are sufficiently good to still get somehow the correct estimates. And that's where somehow the game becomes very complicated, and then it's explaining the last 4 years of work in which progressively we were reaching better and better exponents.
This is always the strategy.
This is all a strategy, yes. And as we will see, the strategy is kind of pretty general. Okay, so now, what is this WC? So this WC is something that I want to add in such a way that this thing is divergence free, okay? So what I will do is I will do something like this. I will take the divergence of VQ plus the big W. Okay, this is non-zero. And then I want to here put an operator. So I want to find a vector field which is small and has this divergence, okay? And then that will be the correction. So here I want to do something like divergence to the -1. Now, this is not a well-defined operator. On the other hand, you see, for instance, where Hopf theory might help you, right? So if I want a vector field which gives you the divergence of something else, right? So one thing I could do is I could, for instance, solve the Laplace equation for some potential, right? I could solve Laplacian of alpha equal to the divergence that I'm interested in, right? And then your WC would be the gradient of alpha, right? So one way of defining my operator over here, if you want to use kind of this type of fancy formalism, I should actually invert minus the Laplacian, I guess. So here I should do something like that, right? And you see the ellipticity of the operator, right? You see, I'm using an elliptic operator. If I have estimates for this side, I will get the estimate for alpha. And what I'm telling you here, I'm not going to give you the computation, because if I'm trying to do it with this operator over here, I actually have to use a fourth order operator. We need the bi-Laplacian. So the formula looks kind of bad. But in the end, it's actually a very nice elliptic operator, and you get the estimates anyway. Okay, so now, of course, when I'm doing this, right, the divergence of VQ is equal to 0, because I was coming from a solution of the Euler equation. So this part actually goes away. So now I have to understand this divergence business over here. Okay? And now you see that something interesting is happening. You see that, so here I will have my operator, which is good, which is giving me the correct thing. And now here I will have the divergence on these low variables. right? Because remember that my ansatz has slow variables over here, and then fast oscillating terms. But then I have the divergence on the fast variables. And the divergence on the fast variable is spitting me this lambda q plus 1, which is, of course, very, very dangerous, right? I don't want that. So I don't want that. I don't want that, and let me call this kind of fast. Or maybe for the fast variables, let me introduce a letter. So let me say the fast variable is psi, and the fast variable time is tau. Okay, so here I will have divergence psi of w is equal to 0. So this I want to kill. So if I want to kill this guy, it means I now got a condition. So you see, by following up somehow similar computations, I will get a set of conditions on my big W. So let me write this condition over here. So this is what we call, I will tell you later why, the cell problem. So the first condition that we got is that the psi divergence of W is equal to 0. OK, now I want to tell you the slow guy does not have the lambda q. Okay? So now inverting the divergence is like integrating. And I have a fast oscillation over here. Right? So if you have something which is, for instance, a periodic function, so if you have that you're periodic in psi, and you are integrating something which oscillates fast, okay, that something becomes small. How small? Of the order 1 over lambda q plus 1. Right? That is almost true. So let me be a little bit more precise. So here you have this divergence law, right? So it's a function of the following variables. So it's something like divergence slope of w, and then you have the q of xt, r circle q of xt, and then you have lambda q plus 1 x, lambda q plus 1 t. OK, so let's think about this as a kind of complicated function of the variable x, t, and lambda x, lambda t. So in particular, if I fix here psi and tau, what I can do is a Fourier expansion in psi of my function. Okay? So if I do a Fourier expansion of this beast, let me call this beast kind of z. So I will get z of something like x, t, lambda q plus 1, x, lambda q plus 1, t. Okay? This is, in Fourier, some coefficients, and I'm expanding in Fourier only in this variable. So the coefficients will depend on x, t, and say tau. Right? So here I will have maybe some coefficients. Let me say a, k of x, t, lambda q plus 1, t. Okay, and then I have e to the I k lambda q plus 1 x dot t. Okay, and now this operator is pretty explicit. And when you look at this operator, which is pretty explicit, right? So I'm inverting somehow. I'm integrating this, and I get a 1 over k lambda q plus 1. Okay, but not quite. Because if I have a constant term, if I have a term with k equals 0, then I will not be able to do anything to that, right? I will not gain any 1 over lambda q plus 1. So that Fourier coefficient has to be kind of killed. Now, what is the Fourier coefficient that I have to kill? Well, of course, it's the 0 Fourier coefficient, so it's the average of w in the psi variable. Okay, so let me then use this notation for it. So this is the second condition. Yeah, that's why we call it cell problem. Yeah. Exactly. But that was actually not our source of inspiration. Something we realized later. OK, now I want to play the same game. And I want to play the same game on the much more complicated equation over here. Right? And now I want to use the following rule of thumb. This operator r, which is like the divergence to the minus 1, is spitting a 1 over lambda q plus 1 every time that applied. Okay? So of course, if I'm doing that, so now r circle q plus 1, which I want to be much smaller, is going to be this operator r. And then here I have I mean, I have a pretty bad expression. And I have, first of all, dt vq plus divergence of vq tensor vq plus gradient of pq. Okay? So this is the equation. Okay? And then I have to take derivatives of the perturbation. So I will have something like fast variables and then and then fast derivatives of w, right? So there will be a guy like this. Then since I have a nonlinearity, I will have something like this. Okay, and then I will have this guy. Okay, and then I have slow derivatives. So now I have the equation for this. So this is the divergence of R circle Q. Then I have the fast guys. And of course, all of this I want to set to 0. Okay, and if you want to set all of this to 0, you see a partial differential equation over here. And that's another condition. Ah, I forgot actually the pressure, right? And then I have the slow variables, the slow derivatives. And somehow the slow derivatives, I want to say that I can ignore them because there is no lambda in front. And then when I am dividing, when I am computing the divergence inverse, I get this 1 over lambda. Okay? But to apply this idea that when I use the inverse the divergence, I get the 1 over lambda, I need this condition on the Fourier coefficient, which is equal to 0.
So your W depends on Q.
Yeah. Well, no. My W is a master function. It will only it will be the same master function every time.
It seems to be what do I read there? VQ?
Yeah. Okay. So my W depends on V, R circle, psi, and tau. Okay. So when I'm using this over here, VQ, and I'm ignoring the dependence on x and t, it's essentially because I'm looking at this function W as VQ as V and R circle. So yes, the W is depending also on the entry V, but it will be defined for all possible velocities, right? So it's and for all possible tensors R circle. So it will depend on V. I think about it as a dependence on V, not really on VQ. Then VQ will depend on x and t, and therefore this will kind of make my function more complicated. Okay. So now to kill the slow derivatives, I need the average condition, right? And of course, anytime that I have W and I'm computing derivatives of W and W is linear, the 0 condition is still going to hold, right? But now you see something interesting, and the something interesting is that my system has resonances, right? So here in the slow derivatives, there will be also one slow derivative, which is interesting, which is the slow divergence of W tensor W. Okay? Now, when I make the Fourier expansion of this quantity, I have resonances. So although the Fourier expansion of W does not have the constant term, the Fourier expansion of the product, of course, will have the constant term. Okay? So I want this actually to be 0, but in fact, that is what I claim is going to help me because I have this one that I want to kill. So what I will actually impose is that the average in psi of this W tensor W is equal to minus R circle Q, so that then it cancels. Okay, so this one will be used together with this one to really get something at which I can apply this philosophy, that when I'm inverting the divergence, I get 1 over lambda q plus 1. And so the final condition looks like this. Okay? So now, coming back to your question. So let me forget that this is VQ. So let me just call this is R circle and this is V. Okay? So I have a function W which is depending on V, R circle, psi, and tau. And I have a PDE in psi and tau and some conditions in psi and tau, but the function is varying in V and R circle. So what I want is a smooth function. In some sense, I have a family of solutions to a given system of PDE, and I have these parameters V and R circle. And what I want, of course, is that W varies kind of nicely in function of V and R circle. So if you want, what I'm looking for is a manifold of solutions to a kind of Euler equation which satisfies some average conditions. Okay, so one thing you should actually protest about, though. This guy is trace-free, and this one is not trace-free. So I certainly cannot achieve that the average of a non-trace-free matrix, actually this is positive semi-definite, and this being trace-free is not positive semi-definite. So certainly I cannot achieve that. But I can achieve that the traceless part of W tensor W is equal to R circle. And why that doesn't damage me? Because the trace of this, when I compute the divergence, gives me a gradient. And that gradient I can stick into the pressure. Okay? So the pressure is not really defined in this way. It's defined in a more complicated way because there is a certain remainder term. Okay? Now, that also tells you why actually the energy is kind of free, in a sense. Because the energy is related to the modulus of this quantity that I'm adding. Okay? So, of course, the energy of, say, the kinetic energy of VQ plus 1 is the kinetic energy of VQ plus this W. Okay? But W is fastly oscillating. So the cross terms, essentially, they cancel. So the kinetic energy of VQ plus 1 is the kinetic energy of VQ plus the kinetic energy which is coming from my W. And what I'm telling you is that the condition is only on the trace-free part. So I can take actually that this condition is correct, but my W, I can take it pretty big or pretty small. Of course, this average condition will tell me I cannot take W too small compared to R circle. So I will need to add a certain amount of energy. But for instance, it's up to me whether this certain amount of energy that I want to add, it is much larger at later time or much smaller at later time. So in particular, if at each step of the iteration, I want to achieve an energy which is, for instance, much larger at time 0 compared to what it is at time 1. Okay? So that explains why in this iteration the energy is kind of for free. Okay, so now what the game seems to be is something like if you satisfy these conditions, so you have a function W which depends on VQ, or actually it depends on V and R circle, and it's periodic in tau, for instance. So this will be on T3 times R. Okay? Then I can hope to run my iteration scheme. So it's not the end of the story. So you actually need some estimates, which I'm not going to be detailed about. So you need some estimates on how this function is depending on V and R circle. Because when I'm telling you that I'm taking the slow derivative of this guy, the slow derivative, of course, by the chain rule, will make the derivative of W appear in terms of the velocity in terms of R circle. Okay? And if those derivatives are too big, then my iteration, my promise that the error term over here is small when I actually invert the divergence is not correct anymore. Okay? So why I'm saying this? I'm saying this because if you just want to solve this system and get these prescriptions, you can actually do it. But if you want to keep correct estimates, then you cannot.
Well, you have to keep estimates, so that you want to keep estimating the solutions, right? You've got to estimate the V's.
Okay, so that actually I will do it inductively. For instance, the v will be converging to a continuous function, so I know how big it is and size and stuff like that. But so I will have some informations about the v's and its derivatives along the iteration. But that's not only what I need also to have information about the v derivative of w and the r derivative of w. Otherwise, this scheme is breaking down. Okay? And actually, what you realize is that you cannot solve this cell problem and get the correct estimates and run the iteration in such a way that all this guy over here is set up equal to 0. That you cannot do. So it's not that difficult to see. So the reason why it took then the last 4 or 5 years to get to the conjecture is because what you can actually do and what is done in practice in older works, you cannot set this identically equal to 0, but you can set it very close to 0. Of course, now the very close to 0 becomes kind of quantitative, and the better you actually set this up to 0, the more you're getting close to the exponent of the conjecture, right? Which is this alpha equal 1 over 3. So each improvement that you see in the literature is a better way to make this guy equal to 0, essentially. Okay. Up to now, where so there were some innovative ideas into the whole concept, but let me not go into that.
So you're saying the recent one was just to set that scheme up in a better way. The improvements in the last few years.
Yeah. Okay. So the improvement in the last few years is still using sort of this iteration mechanism. But you cannot set up this identically equal to 0. So what actually happened is people have improved more clever choices of w. So this was up to something like the exponent 1 over 5, then yet another clever choice of w. And then at a certain point, the key idea of EZ was actually that you can make this error, you can actually make it compactly supported in time in small time intervals. And that kind of closed the proof. So that was the essential new ingredient that he had. So up to that, actually, it was more like trying to optimize on this w. Yes. Trying to optimize on this w, for instance, meant that here there is something better than this ansatz. Instead of making this ansatz, you actually substitute x with the flow of the vector field vq, for instance. And when you substitute with the flow of vector field vq, this transport part, for instance, gets equal to 0 automatically. Okay, so it was on bettering the ansatz, but in a non-trivial way. It was not only a technical work. Okay, so now I've explained you what is the basic iteration mechanism. I've explained you why the energy seems like something that you can actually modify as you like. It will have some constraints, of course, which are related to how big is this R circle Q at each iteration, but you're free to add much more energy to a solution. So now let me tell you why this exponent 1 over 3 seems very, very reasonable. If you were able to set up an iteration in which this is identically equal to 0, okay? Good. So let me go back to this RQ plus 1. Okay, so here I have something like my operator R. So the operator is not seeing this guy. It will not see this guy. It will not see the lambda q plus 1. So the operator R will only see the slow derivatives. But there's also one term that you're going to see, that is, when you are expanding this quadratic, when you're doing the quadratic expansion over here, right? So I have something like divergence of VQ tensor VQ plus W tensor VQ plus W. It gives you two terms. So there is the divergence of VQ tensor VQ. Okay, there is the quadratic part, which I already took into account. Then there is this guy, right, which you see appearing here. Then there is the slow derivative, but I'm going to ignore it. But then there is also this one. Okay? So now I'm claiming this is actually the most dangerous term. And I'm not going to tell you why. But it is that way. So this is dangerous because it's taking the derivative of the previous iteration. Right? And certainly the derivative of my function has to blow up as I go along the iteration. So why it has to blow up? Well, because I know I cannot run this iteration above Hölder exponent 1 over 3, right? So I cannot hope to have actually a bounded derivative. Okay, so in a sense, you could say, well, if I believe my ansatz, that this guy is giving me back a 1 over lambda q plus 1, okay, then here I have a certain error, and this certain error is essentially the size of the derivative in C0 and the size of big W. And the size of the big W is the difference between the next function and the function that we had before. Okay, now let me elaborate a little bit more on that. So actually, you see from this condition that the size of W has to be essentially the size of this, the square root of the size of R circle. And this is R circle from the previous iteration, okay? So what you really have here is an estimate which looks like this. Okay, so now assume your R circle Q has a C0 norm which has a certain size. So let me call it delta Q. And this is going down to 0. Okay? Actually, let me call it delta Q plus 1. Sorry. And the reason will be apparent in a moment. So what I also just told you is that the size of the difference between VQ plus 1 and VQ is delta Q plus 1 to the 1/2. So that's the reason why I'm calling this guy delta Q plus 1, right? So because this size is essentially the size of W, which I told you is realistic to expect it's going to be the square root of that guy. Okay, now.
Why is that the square root of delta? I'm sorry.
Sorry?
Why is that the square root of delta again?
Well, because here you have a quadratic equation to solve, right? So you want to solve something like W squared is equal to R circle. Now, that you can do it as the square root of that guy, it's of course if you do things carefully and optimally. But certainly you cannot do anything better, right? I mean, if this guy is of size 1 over a million, you will not be able to get this better than the square root of 1 over a million. So that is a kind of best bound that you can hope for, okay? So in all of this business, I'm just hoping for the best bounds for all the best things happening, and then I'm getting at the conjecture. And somehow if you had asked me like 10 years ago, what I found miraculously is that actually all of these guys, they align, and they actually, all of the things that could be sharp, actually they are sharp, and they finally, you finally get there, which, if you had asked me a few years ago, I would have actually doubted very much that this is possible. Okay, now, of course, in this estimate, right, what is important for me is that I have to compute the inflation of the C1 norm, okay? So now, of course, what I know when I am computing this derivative, well, I know that I am computing the derivative of something which in C0 has the size delta Q plus 1 to the 1/2. But then, if you remember, I'm oscillating, and I'm oscillating like lambda Q plus 1. Of course, when I compute this derivative, I have a very complicated formula to take into account. I have to take the derivative of that big W, right? But the danger is all on the fast oscillating variables. So essentially, it will spit something like delta Q plus 1 to the 1/2 lambda Q plus 1. Okay? Because W is of the size delta Q plus 1, and then I will have a derivative of W, which is of the size of delta Q plus 1 in the other variables, and then it's multiplied by lambda Q plus 1. Okay? Of course, this means also that, here you will see that I need certain estimates. On W, for instance, I'm just saying the derivative of big W independently of VQ and R circle Q always stays bounded. the derivative in the fast variable. Okay, so that's one type of estimate that I'm assuming. Now, okay, any decent iteration which is producing some solution to the PDE, you hope it's going down at least exponentially fast, right? For instance, if you're hoping that you are converging in C0, you're hoping that you have a summable series. So an exponential convergence is maybe not too bad to hope. In fact, you can run this game even with a double exponential convergence. So if this one is going down exponentially, this one has to blow up exponentially, because we already know that we cannot keep the C1 norm under control. Okay? So, but if this one is blowing up exponentially, this means when I compute the derivative of VQ plus 1, I see a finite terms of a geometric series which is exploding. Okay? So the size of this guy is essentially the size of the last summand, because I'm just summing a geometric series which is exploding. Okay, so now you see what I want to do. So I assume I have these bounds. Now to close the argument, I have this bound on R circle Q plus 1. So the bound is, this is less or equal than 1 over lambda Q plus 1 delta Q to the 1/2 lambda Q delta Q plus 1 to the 1/2. Okay? Now, what I get to be consistent with my scheme should be smaller than delta Q plus 2. Okay? And this is the bound I have. So, of course, if I can say that this is smaller than delta Q plus 2, so if I have this condition, okay, then I have closed my iteration. Then I can simply keep going. Okay, so in this scheme, what is the regularity of the final object? Okay, so I have this estimate. I have this estimate. Of course, now by interpolation, if I'm looking at the Hölder estimate, I will have this estimate. Right? So let's say I have some threshold, right, for which I can prove, below this threshold I can prove actually that this series is summable, and above that threshold I cannot prove that that series is summable. Okay, so the threshold that you could guess is a threshold where delta Q to the 1/2 is exactly equal to lambda Q to the minus alpha. Right? So that actually these two guys, they cancel and they get essentially equal to 1. Then, I mean, they are going like, I mean, this is exploding like an exponential. This is converging like an exponential. So if I take a slightly smaller alpha, then I will actually have a convergent series. And if I take a slightly larger alpha, then I certainly have an exploding series. And I mean, on this kind of critical situation, I don't know, right? Because maybe I can squeeze a log and they can still converge. Okay, so this gives me a relation, which is delta Q equal lambda Q to the power minus 2 alpha. Okay? And then I'm assuming that this lambda Q is exploding like an exponential. So let us simply fix, say, lambda 0. Let us call it lambda, and let us say that I have this law. Okay? Well, now it's a back of the envelope computation, right? So I have these numbers, delta Q, lambda Q. I want this inequality to be respected. I'm assuming I have this relation. Let me see for which alpha I can hope that this is satisfied and that one is satisfied as well. Okay, this is a back of the envelope computation that is not even a calculus 1 computation. It's a high school computation, which I'm going to give you in the next few seconds. And then you will see this magic exponent 1/3 coming out. Okay, so let me insert this lambda to the power minus 2 alpha Q inside there, right? So, okay, so I have delta Q to the power 1/2, so that is lambda to the minus alpha Q. Then I have lambda q, which is lambda to the power q. Then I have delta q plus 1 to the 1/2, which is lambda to the power minus alpha times q plus 1. And then I am dividing by lambda to the q plus lambda q plus 1, which is lambda to the power q plus 1. Okay, and then I have delta to the power q, delta q plus 2, which is lambda to the power minus alpha times q plus 2 minus 2 alpha, sorry, because I don't have the square root. Okay, and now you see what is very nice, right? So the q goes away. So let me look at the exponents, right? So the q goes away. I have a minus alpha q, and it goes away with minus 2 alpha q. So they balance also. So you will see I have minus alpha plus 1 less or equal than minus 4 alpha. Sorry, minus 1. Yeah, because that is in the denominator. Okay, pull 4 alpha on the other side and 1 on the other side. And there you go. So this is the condition. Alpha equal 1/3 is critical for this iteration. Okay, so that in a nutshell is the back of the envelope computation that we did in 2008, essentially, which was convincing us that this direction could be possibly leading to solving that problem. And that's it. Thank you.